So in this session, we'll be learning about the continuation of deadlock. So as we have seen, deadlocks are especially for a limited number of resources are available, finite number of resources are available, but there are many processes. So therefore, there is a much demand for resources. Resources can be consumable, resources can be reusable. So how do you know that deadlock is formed? What are the characteristics are needed to form a deadlock? So to form a deadlock, what are the characteristics are needed? So let us see, you also can able to observe very clearly, is there any deadlock formed or not? So there is a P1 is requesting for resource Rx, but Rx do not have any free copies because one copy is already given to process P2 and P2 is requesting for resource Ry and resource Ry has two copies. One copy is given to P1 and one copy is given to P3. Can you imagine that? Is there any deadlock? Is there any deadlock? You can comment your answer. You can comment your answer. Don't think that there is a cycle because actually there is a cycle. I agree. There is a cycle among this P1 Rx, P2 Ry, and P1. But I will reveal the answer. What is the answer? One copy is given to P2 here, and one copy is given to P3 here, and one copy is already given to P1 here. What is the meaning of that? Let me write the solution here. Ry is given to whom? One copy is given to P3 and one copy is given to P1. Okay. Then Rx, what is the meaning of that? One copy is given to P1. No, one copy is given to P2. That's it. So P1 requesting for one copy of Rx. P1 is requesting for one copy of Rx, but that one copy of Rx is already given to P2 according to this case. But P2 needs one copy of Ry. P2 needs one copy of Ry, but Ry is given one copy to P3 and one copy to P1. But imagine there is a cycle among P1, Rx, P2, Ry, but P3 is excluded from there. What does it mean by that? P3 is executing, it's continuing its execution because it do not need any other resources except one copy of Ry only. So it is granted because already it is allocated to P3. P3 successfully completed its execution. Just you are requesting only. It is already allocated. It is already allocated. And in this case, it is already allocated. Don't think that there is a cycle. There is a cycle among all the processes. Soon after P3 is not interested for any other resource except Ry one copy. Soon after P3 executed, soon after P3 completed its execution after some time, P3 completed its execution. That's it. Then when it is executed, it is removed from the queue. OS will remove it and one copy will be released back. One copy is released. One copy is released. When that copy is released, observe carefully. This copy is released. This is a busy. I agree. This is a free now. Earlier it is a busy. Now it becomes a free. And this is what? Busy. Now, whatever the resource becomes free, that resource is asking by whom? That resource is asking by whom? P2. Then immediately the P2 will get a chance of Ry. P2 will get a chance of, so P2 is asking for one copy of Ry, right? P2 will get a chance of Ry. That's it. Then P2 is executing one copy of Ry. Then the other one copy of Rx, it get completed. When it is completed, P2 releases back one copy of Rx, and P2 releases back one copy of Ry. Then P1 is requesting for one copy of Rx, and that one copy of Rx becomes free, then it is allocated to P1. So that's why in this case, no deadlock situation. So what are the important things I have shared? Important things I have shared. Observe. First, who is completing its execution? First step, P3 finishes its execution. After that, who is getting execution? P2 is getting execution. After that, P2 releases its resources. P1 gets execution. This is the order. First P3 will execute and give its copy back to Ry. Then that copy will be allocated to a P2. P2 is using Rx one copy and Ry one copy, and P2 will execute. Then after that, Rx will be released. That Rx will be given to P1. Then P1 successfully completed execution. This is what. Now that's why. How are you going to say that there is a deadlock is formed? Deadlock is formed because of three important conditions. One condition is mutual exclusion. Mutual exclusion is nothing but only resource can be utilized by only one process. Resource can be utilized by one process. Resources cannot be shared. In real example, only one car should go. Only one car can occupy a road segment or intersection space at a time. Two cars cannot use the same space simultaneously. So that resources can be given to only P1, and P1 is requesting for Ry, but unfortunately Ry is given to P2 and P2 is requesting for Rx. So in this case, it is forming a deadlock because resources are not shared. Only one copy, they are binding each other. If there is a one copy is available here, then there will not be any deadlock. There will not be any deadlock because that copy is freely available. That copy, whoever is requesting, P2 is requesting so that you can assign it. P2 will pass it execution. There is no cycle formation in this case. Hold and wait. So what is a hold and wait? There is a process P1. It is holding Rx resource. It is holding Rx resource. Holding means it should be from resource to process. Holding Rx, but this there is a process P2. There is a process P2. This is a resource Ry. This is a resource Ry. So Ry is given to P2. So P2 is holding in this case, and P1 is requesting for Ry. P1 is requesting for Ry. It is not possible because already Ry is given to P2. Then your requesting edge becomes a waiting edge. Your requesting edge becomes waiting edge. Either it should convert it into allocated edge or it should be converted into waiting edge. As the Ry copy is not available, then your request will be under waiting because it is not validated. Then in this case, P2 requesting for Rx, but Rx is already given to P1. Therefore, P2, whatever the request is coming, then you're supposed to be under waiting. So this is what is the meaning of hold and wait. You hold one resource and waiting for other particular processes which are already holded those resources. This is called hold and waiting. Holding some resource and waiting for some other resource. If it is freely available, no issue. Otherwise, you are going to put it under where? Waiting. No preemption. What is the meaning of preemption in this case is, so you cannot forcefully you cannot forcefully preempt or suspend any kind of resource. You cannot forcefully preempt or suspend any kind of resource. So what does it mean by that? So let me show you here. There is a P1 or resource Rx, which is already given to P1. See, observe, even I am changing the positions of process and resource. Don't get confused. That's why I'm writing different styles. What is the edge? You can comment. What is the edge here? The edge is as it is coming from resource to P1, which indicates that it is assigned. It's granted. And there is a resource Ry. There is a resource Ry, which is a given arrow to P2. What does it mean by this? It is granted. That means it is assigned. Ry is assigned to P2 and Rx is assigned to P1. Now, as usually, we will keep a log them. P1 is requesting for Ry and P2 is requesting for Rx. So we are making it lock. We are making it a circular loop. Then in this case, they are going to be what? Waiting because Rx is not available. Here P2 is also under waiting because Rx is not available. In this case, P1 is waiting because Ry is not available. So I can clear the deadlock situation. I can confirm that it is a deadlock, no issue. But I can clear this deadlock using a preemption concept. What is a preemption? If I suspend any of the process, if I suspend any of the process or any of the resource, for example, I suspended P1. So I am forcefully kill the P1. Then what happened? What happened? Whatever the resource is given to P1, P1 already hold what? Rx. That Rx will be recovered. That Rx will be recovered because P1 is not there in the race. Because you have killed it, you have preempted it, or you have suspended it. Killed means removal. Suspended means pause. Afterwards, you can play it like high priority versus low priority. So once P1 got preempted, then whatever the resource you have allocated, one edge, right? So one copy you have assigned to P1, that one copy will coming back to Rx. Now who are active right now? Rx is active and Ry is active and P2 is active because P1 is not in the race. So whatever the copy has come, observe, one copy has come. Whatever the copy has come, that copy is freely available so that I can give it to P2. So P2 waiting edge will be removed because this becomes which edge? Assigned edge. So this is assigned, Rx is assigned and Ry is assigned, then P2 could able to complete its task. So you may get a doubt that which process I should attempt, preempt. Our operating system is doing a preemption on P1 or P2. That depends upon certain conditions. Whether P1 is just started or P1 is already reached to about to completion stage. If it is just started, you remove P1. If it is already about to complete, don't remove P1. Unnecessarily, you are going to waste the resources which are already allocated to it. So, whichever process has just recently started, you can kill it. Or whichever the process has got what? Lowest resources, then you can kill it. Or sometimes the operating system thinks such a way that a process is started with a huge number of resources, but those resources are demanded by some other process. In such case, you can suspend that particular process because huge number of resources of different varieties can be scattered to other particular processes. Third one is a circular wait. What is the meaning of circular wait? It should form a circular wait. So it should form a circular wait concept. So again, let me write the graph here. There is a process P1 and there is a process P2. So P1 is requesting for a Rx. Assumption, no copies are available. I'm not writing any dots there because Rx is already given to P2 and P2 is requesting for Ry there are no spaces are available because it's already given to P1. So this is circular wait. What is it? Rx is given to P2 and P2 is requesting for Ry. Ry is given to P1 and P1 is requesting for Rx. So in this, what are assigned edge? Red colors are assigned because resource to process. Resource to process is already indicates that assign, and process to resource, it indicates that what? Request. It indicates the request edge. This is assigned edge. So these are the four conditions. What are the four conditions? Mutual exclusion. And second condition is hold and wait. Third condition is preemptions cannot be applied. And the last condition is it should form a circular wait. If any of the condition is broken, then there is no deadlock. Simple blind answer you can give to interviewer. If any of the condition is broken, then you don't see a concept of deadlock in operating system concept. All four should occur because they are interdependent each other. When hold and wait is there, automatically circular wait will be happening automatically. So these are the four conditions or characteristics to say or confirm that there is a what? Deadlock happen.